Hi, hello students. Welcome back to India's most comprehensive online learning platform, BYJU'S Exam Prep. This is Anil Prasad Surumpudi, and in this session, we are going to cover the remaining topics of the operating systems. Okay. In the yesterday's class, we did we already dealt with some of the topics. In today's session, we are going to deal with the other topics that are remaining in the operating systems for the upcoming BARC exam. So once again, let me invite you to this session in which you will be given the in a quick recap of the entire operating system. Half done yesterday, half is going to be done in today's session. So to start with, this is Anil Prasad Surumpudi, and I do have a total of 13 plus years of experience in which I've been training the students for the GATE exam and the other competitive exams all over the India, including right from Andaman and Nicobar till Srinagar, everywhere in India. And for the past 5 years, I've been organizing more than 1,000 plus seminars towards the career guidance. And my subject of expertise is I'm an expert in computer architecture, operating systems, programming data structures, and compiler design. So very good evening, all, one and all. And I want you people to take this Byjus scholarship test. I would like you to know that if you attempt the Byjus scholarship test, there is a possibility that you can get 90% of all the courses in the Byjus platform. So why waiting? Scholarship test is coming live on 10th March 9 a.m. to 9 p.m. So do not miss this opportunity. Register for scholarship test right now and attempt it. And if you can score good, you will be given 90% of discount, 90% off on all the courses across the platform. And one more exciting news, I just am coming live on your way on 13th of this March, 7:30 p.m. for a session on a preparation strategy to crack the GATE 2025 exam within one shot. Because most of you students are maybe preparing for GATE 2025, 2026, but when it comes to the guidance, you are, let me tell you that you people are not properly being guided. If you can be given a proper guidance, I'm sure you will be able to crack the GATE exam in one shot with a very good rank. For this reason, to address this problem, I'm coming live on 13th of the March, 7:30 p.m. to give you all the tips and tricks to guide you in every possible direction to crack the GATE exam in one shot. And we already started a ground zero series in which we targeted the students who are appearing for the GATE 2025. And the objective of ground zero series is to have the students basics perfect, because unless we make our basics perfect, it is not quite feasible to appear for the GATE exams. So this is the thing. And let me straight away get into the session because it's been some delay. Yeah. Now, there comes your first question. The first question is, consider the following policies for preventing the deadlock system with mutually exclusive resources. Here the first question is all about deadlocks. Now let me tell you, before I get into the actually to solve this question, let us understand about the deadlocks for one more time. What exactly is a deadlock? Let me tell you. See, when it comes to the operating system needs to deal with a set of resources which are limited. The resources that are connected to the system are very limited. What are the possible resources for a system? Hi Samir, very good evening. Yeah. What are the resources of a system? Let me tell you about the resources. When it comes to the resources starting from CPU time, main memory space, and the third one is IO devices and files. Okay, these are all the resources. These resources are pretty limited because when it comes to the resources are very limited, but the contenders for the resources will be more. Every process during the execution may require some or the other resources, but understand carefully, these resources must be utilized in a mutually exclusive fashion. That means if I'm using one resource right now, operating system should make sure that nobody else is actually going to use the same resource as I am using right now. So this is what mutually exclusive feature of the resources, property of the resources. So here the operating system will have a huge overhead, huge burden on resource sharing. A resource which actually is given to some program should not be allotted to some other program or some other process. This is what a mutually exclusive resource property of the resources. Now, what is the deadlock? Deadlock is something in which I need some resources which actually are held by some other process which are blocked. So I will never be able to go ahead with my execution. For an example, I require one resource, and that resource which I require right now, which actually is held by some other process which actually is blocked. When that process will be released from the blocked state, nobody knows. So that means that we both people will be in the deadlock state. Neither the other process can continue nor myself will continue. This is one of the example for the deadlock. Now the thing is, how we will be able to avoid the deadlock, how we will be able to prevent the deadlock. I'll tell you, there are a lot of prevention schemes for the deadlock. And first of all, in order to understand the deadlock prevention scheme, we need to understand about the 4 properties of the computer system, 4 properties of the operating system. There are 4 conditions. There are 4 certain conditions we must understand. Those conditions, let me take here, I will take it. Those conditions are, first one is mutual exclusion. I would say mutex. What is the mutex property of a resource? Mutex property of a resource states that when a resource is allocated to some process, at the same time that resource cannot be allocated to some other process. This is what mutual exclusion property of a resource. Second one is hold and wait. What is hold and wait? Hold and wait is the condition that occurs when a process holds some resources and waiting for some other resources which are held by some other process. This is called a hold and wait condition. In the hold and wait condition, there is a possibility of the deadlock. And the third one is a circular wait. What is circular wait? Circular wait is there is a set of processes which are arranged in a circular fashion. Rather, there is a set of processes which are labeled as 0 to 4. Total 5 processes. Now, the thing is, the resource which is required by the first process held by the second process, the resource which is required by the second process held by the third process, the resource which is required by the third process held by the fourth process, the resource which is required by the fourth process held by the first process again. Now, there is a circular wait. The resource which I want actually is available with my next guy. The resource which my next guy wants is actually held by the guy who sits adjacent to him. So if there comes a circular wait, that is called a condition of a circular wait that existing in the system. This is what the circular wait condition of a system. Fourth one is no preemption. What is no preemption? When a resource have been allocated to one process, unless the process releases voluntarily the resources, voluntarily the resource that it held, operating system cannot preempt, cannot pull those resources back. For an example, I am the operating system. I have given a resource printer to one process Px. There is a printer P1 has been assigned to the process Px. This is the printer, this is the process. Now process P1, printer P1 has actually been assigned to process Px. Okay. Now, what is no preemption? No preemption states that when a resource has actually been allocated to one process, unless that process releases the resource, operating system cannot forcibly pull that resource back. This is called no preemption. Now let me tell you, in order to have this deadlock occur in any system, all these 4 conditions must be simultaneously held in the system. That is, let me tell you, just clear this. Mutual exclusion, hold and wait, circular wait, and no preemption. If all these 4 conditions are simultaneously held in any system, then that means that the system may have a chance to get into the deadlock state. So now the thing is, in order to prevent a deadlock, if you think sensibly, the wonderful deadlock prevention scheme is at least avoid one of these conditions. So the system will never enter into the deadlock state. If you can avoid at least one, the system can never enter into the deadlock state. What are those? Anyhow, let me tell you, mutex can never be avoided. Mutex, that means the property of the mutex. when a resource has actually been assigned to one process, at the same time, simultaneously, the resource cannot be assigned to some other process. This is mutex, and this should always be adhered by the operating system. It should not be violated. Mutex should be satisfied under every circumstance. Now, hold and wait. We can avoid hold and wait by possibly using one or the other algorithm. Hold and wait can be avoided. Circular wait can be avoided. No preemption can also be avoided. Okay. Now, in this slide, let us see. Which are the possible options or the correct options. Process should acquire all their resources at the beginning of the execution. If any resource is not available, all the resources acquired so far are released. Now the thing is, this is one of the algorithm that can avoid no preemption. Initially, when a process requires any resource, immediately it should ask for. Before the starting of its execution itself, it needs to ask for the resources. If any of the resources are not available, then all the resources which have actually been assigned can be preempted. So no preemption can be satisfied by this condition. Second one is, the resources are numbered uniquely and the process are allowed to request for the resources only in the increasing resource number. So in this case, what is the second one? If you recall, second one actually, by using the second algorithm, if we realize an algorithm by the second statement, we will be able to avoid circular wait. In order to avoid the circular wait, what we need to do is, all the resources must be numbered. All the processes must also be numbered if you want. But any process, if it wants resources, it must only request for the resources in the increased order. It needs to ask for P0 followed by P1 followed by P2, not in the reverse direction. If you use this algorithm, no preemption. A circular wait can be avoided. And the third one is, the resources are numbered uniquely and the process are allowed to request for the resources only in the decreasing resource numbers. Of course, this is also another mechanism to avoid the circular wait. Circular wait can be implemented in two ways. A process may request for the resources either in the increased chronological order or in the decreased chronological order. So by using 2 and 3, we will be able to avoid the circular wait. The resources are numbered uniquely. A process is allowed to request for the resources only for a resource with a resource number larger than its currently held resources. Which of the above policies can be used for preventing the deadlock? Which is the correct one? Just a minute. This is not a valid scheme, because in the fourth, if you can look at carefully, in the fourth, it is saying that we need to ask for a resource, and any process is allowed to ask for only one resource at a time, which is quite not possible. So 4 is not the correct option. Let me go to the next one. Consider the procedure below for the producer consumer problem which uses the semaphores. Okay, so you already might have known the semaphore. Yesterday also we discussed about a semaphore. When a semaphore S is being used, there can be two operations performed on the semaphore. Semaphores are primarily used to protect the critical section, protect the shared access to the resources. When you perform wait operation on a semaphore, it will get decremented. If you perform signal operation on a semaphore, it will get incremented. Now, here he is suggesting a solution to the producer and consumer problem by using the semaphore. It is a customized solution for the producer and consumer problem. How will we be able to identify? Of course, when you look at the screen, you can clearly see there is a problem with the solution. I will tell you the solution. Here the thing is, initially there is a semaphore N initialized to 0. There is one more semaphore S which is initialized to 1. Okay, there are two semaphores used. One semaphore N is initialized to 0. Second semaphore S is initialized to 1. Now, void producer and void consumer. Producer says during the production, he is going to perform wait operation on S. If he is successfully able to perform this wait operation on S, if he is not blocked, he will be able to add an item into the buffer. After coming out, he needs to release signal operation on S, and he need to release he need to perform signal operation on S. He also need to say signal operation on N. Okay. Now, when it comes to the consumer, while 2, he is going to perform a signal operation on S followed by signal operation on N, remove from the buffer. If we successfully execute these 2 statements, that means if he is not blocked after executing signal on S and signal on N, he will be able to perform consuming an item from the buffer. Then he is going to perform signal operation on S, and then he will be able to consume. Okay, here if you recall carefully, directly you can see a problem. The thing is, you already knew producer and consumer will be using a shared buffer. Let us say the buffer size, there is some elements in the buffer, 1, 2, 3, 4, 5. Now producer consumer, when you look at carefully, first of all, producer must be able to produce for the consumer to consume an item. If there is no item in the buffer, consumer will not be able to consume the item. So producer and consumer should be executing in a proper order. First, producer should execute, followed by the consumer. Producer should execute, followed by the consumer. Consumer cannot execute prior to the scheduler producing at least one item, right? So when you have a look at, see, even the consumer gets scheduled, he should be blocked. That is what the rule of the producer and consumer, right? Now let us see, under one circumstance, under some timeline, let us say consumer got scheduled. Now by the time producer did not get scheduled at all, producer did not produce even a single element into the buffer. So at that time, what may happen here? Let me tell you. Consumer, of course, he will come here. After coming here, he just is going to initially execute signal on S. Now what is the S value? S value is equal to 1. When the consumer executes signal on S, S value becomes 0. Did you get me? So in a concurrent system, after executing every line, any process can be preempted. Now understand a scenario. Consumer executes this statement and got preempted by the operating system. Now producer enters into the system. Now producer got scheduled. Now what is the job of the producer? Producer should be able to produce an item into the buffer. What will happen to the producer? Let us have a look at. Now when the producer gets scheduled, he is going to perform a wait operation on S. But is S available? No, S is not available. S is actually held by the consumer. Okay, now the producer will get blocked. I would say producer will be blocked on S. Now when the consumer comes back, he will perform signal operation on N. When he performs signal operation on N, sorry, this is wait operation. This is also wait operation. There is a printing mistake. Wait operation on S and wait operation on N. Then consumer performs wait operation on N. Obviously, consumer will get blocked on N. So there is a mistake here. Let me erase this completely. These are not signals. These are wait. Both are wait. Wait on S, and this is also wait on N. This is what the previous question is. Now when the consumer comes in, initially he is going to perform wait operation on S, where S will become 0. Then he leaves the system. Then the producer comes. When the producer comes, he needs to perform wait operation on S, on which he is going to get blocked because S is not available. S value is already equal to 0. When wait operation is performed, S value will become -1. After which producer will get blocked. When the consumer comes back, consumer will get blocked on performing wait operation on N, because N is already equal to 0, right? So under which both producer and consumer will completely get blocked. Okay, so what are the possible options here? Which one of the following is true? The producer will be able to add an item into the buffer, but consumer can never consume it. This is not correct. The consumer will remove no more item than one item from the buffer. This is also not correct. Deadlock occurs if the consumer succeeds in acquiring the semaphore S, while the buffer is empty. When the buffer is empty, if the consumer gets scheduled, then there will be a deadlock. This is what just we have witnessed, right? So the deadlock occurs if the consumer succeeds in acquiring semaphore S when the buffer is completely empty. So this is option C is the correct option. The next question is, a computer system has 6 tape drives with n processes competing for them. Each process may need 3 tape drives, the maximum value of n for which the system is guaranteed to be deadlock free. Now a system has 6 tape drives. Okay. Now, in order to avoid the deadlock, I told you one rule in the yesterday's class. What is the rule? Simple. The rule is, in order to avoid the deadlock, system needs to have the sufficient number of the resources. So what is the sufficient number? The rule is, system needs to have, first point, at least one process total resource request must be satisfied. Second point is, for remaining processes, their total resource request minus 1 should be satisfied. Okay. So for each other process, if they are asking for 5 resources, for each process we should be able to give 4 resources. So the system needs to have sufficient number of resources to satisfy these criteria. Okay. So what is the total number here? Computer system has 6 tape drives with n processes competing for them. Each process may require 3 tape drives. What is the maximum value of n for which the system is guaranteed to be deadlock free? Now let us take n is the total number of processes, right? Let us take n is equal to 1. Okay. So for 1, obviously there will not be any deadlock because the total number of the resources are far more than the maximum number of requests, which is equal to 3. Even for n is equal to 2, simultaneously, even if we provide the total resources for all these 2 processes, system will have sufficient number of resources because each of the processes will require only 3 resources. Then 2 into 3 is equal to 6. So at the same time, we can provide the resources, the available resources to these 2 processes. Let us take 3. If you take 3 processes, also it is sufficient because at least for 1 process, we require to satisfy all the resource requirement. Plus, for the remaining 2 processes, we should be able to satisfy the remaining resource, total resource requirement minus 1. So, which is equal to 1 into 3, 3 plus 2 into 2 is equal to 4. The system needs to have 7 resources if the total each process may require 3 tape drives. So 1 if we give 3, the maximum number of processes can only be equal to 2 but not more than this. Okay, if the system has 3 processes, then what will happen? Process 1, we need to give all the 3 resources. For the process 2, we need to give 3 minus 1. For the process 3, we also need to give 3 minus 1. So 3 plus 2 plus 2 is equal to system must need to have 7 resources. So the maximum number of processes should only be equal to 2 to avoid a deadlock. Which of the following is not a valid deadlock prevention scheme? Release all the resources before requesting a new resource. Yes. By using which we can avoid hold and wait. Number of the resources uniquely and never request a lower number of resource than a last request. Yes, this is going to avoid circular wait. Never request a resource after releasing any resource. No, it is not possible. It is meaningless. It is senseless because never request a resource after releasing any resource. Is there any meaning for that? That means once after a process releases the resource, it should not ask for any more resources. That can never happen under no computing environment because Obviously, when a process is executing, it may require several resources, right? So the C obviously is the wrong option. Request and all required resources be allocated before the execution. This also is an algorithm which prevents hold and wait. Okay, never request a resource after releasing any resource is the correct answer for this. Next question is, let M0 to M4 be the mutexes, which are the binary semaphores, and P0 to P4 be the resources. Suppose each process Pi executes the following: wait operation on M of I, wait operation on M of I plus 1 mod 4, and followed by the critical section. This is called a critical section. Release on Mi, which is earlier held by this process, held by the current process, and it is going to release the next semaphore which actually has been held by itself. Now, if you look at this carefully, this is the solution for dining philosopher's problem. In the dining philosopher's problem, in order to avoid the deadlock, rather, in order not to have any process block, we need to find out some solutions. The first solution that comes into anybody's mind is to use a semaphore. But if you do not use the semaphores carefully, it leads you to deadlock, especially for the dining philosopher's problem. Here what he is saying, M of I. Okay, what is M of I? M of I meaning the first mutex semaphore. Now what I am doing is, I am the first process, I am 0th process. I am going to hold my first semaphore, which is towards my left, and then I need to grab my right semaphore, which is towards my right. Okay, so after taking both of my semaphores, I will be able to enter into the critical section. But here you can see the biggest problem. What if every process is successful to hold wait of M of I? Then there will be a circular wait, because I will hold my left semaphore. Before I take my right semaphore, I will be preempted, and my next guy also is there is a possibility that at some point I will hold my left semaphore, and my right semaphore is actually the left semaphore, my left guy. My left guy will hold his left semaphore. So everyone is successful in holding their left semaphores. So this actually leads to a circular wait, which is actually a deadlock. Okay, so this leads to a circular wait, which is a deadlock. I hope you got the point. If you do have any doubts, you do please ask me. This is a solution to the producer-consumer problem by using the semaphore. But this solution has a serious drawback of having a circular wait. Every process is successful, may be successful at one point, grabbing their right fork. Forks are protected by the semaphores. Grabbing their left semaphore. Before grabbing the right semaphore, what if they get preempted? The other process which is sitting left to it may get scheduled, may be successful in holding its left semaphore. So every process during this process will be successful in grabbing their left semaphores. That means there will be a circular wait which leads to a deadlock. Next question. The total size of the address space in a virtual memory system is limited by what? The length of MAR, the available secondary storage, the available main memory, all of the above. Understand? What is the address space? Address space meaning what? When it comes to the virtual memory gives an illusion that your total secondary memory is your main memory. But there is no possibility. Our main memory is way too limited than the secondary memory. But in virtual memory, programmer will be given an illusion that he has the total secondary memory available at the disposal physically. Now programmer thinks that the secondary memory hard disk is actually connected at the slot of the main memory. So he thinks that, let us say my secondary memory is equal to 1 GB. My main memory is equal to, let us say, secondary memory is equal to 1 TB. Main memory is equal to 4 GB. What is my main memory? What is the total amount of the memory I can use to execute the programs, run the programs? Only 4 GB. Okay, but in the virtual memory system, the programmer will be given an illusion that the total secondary memory is your main memory. So the programmer will think that 1 GB is his main memory, actually is the address space. So the address space in the virtual memory is nothing but the available secondary storage. I hope you got a point. Next thing is, locality of reference implies the page reference being made by a process. Now let me tell you what is the locality of reference. Locality of reference meaning the cache memory is a wonderful example for the locality of reference. Why do we require the cache memory? What are the things that are going to get stored in a cache memory? It's very simple. Cache memory is going to hold the items that are just being accessed, that are concurrently being accessed. That means cache memory will only hold the concurrent data elements. That is what locality of reference. There are two kinds of locality of reference: temporal locality, spatial locality. What is temporal locality? Temporal locality states that the current data item which is being accessed by the CPU may be required by the CPU in the near future. That is what temporal locality. What is spatial locality? Spatial locality states that in addition to the currently accessed elements, CPU may also require several other elements which are closer to the current element, which is called spatial. But anyhow, when it comes to the locality of reference meaning, it will always be the page used in the previous page reference. Meaning, just a short while ago, when I use a page, that page will also be used in the near future, very near future. That is what the locality of reference. It is likely to be one of the pages used in the last few page references will always be one of the pages existing in the memory. It is not a locality of reference, will always lead to a page fault. No. Okay, locality of reference states a possibility of reusing a page by the CPU, which is recently accessed by the CPU. Now let us say CPU currently accesses the pages. Initially it accessed first one, second one, fifth one, and the sixth one. Now if CPU has to access the next page, there is a possibility that the CPU may ask for one of these pages which have actually been accessed most recently. That is what the locality of reference. Locality of reference states that if the CPU wants a page, most of the times that will be falling in one of the few pages that have been accessed by the CPU. That is a possibility, that is not guaranteed. Okay, CPU may also ask for some other pages. So for which A will be completely ruled out. Will always be the page used in the previous page reference. No, it is not always guaranteed, but sometimes it likely to be one of the pages used in the last few page references. Option B is correct in terms of the locality of reference. Which of the following are the advantages of the virtual memory? Why do we use the virtual memory? Faster access to the memory on an average. No. Virtual memory actually reduces the access time, increases the access time. Faster access directly be violated. If there is a virtual memory system, that virtual memory system always takes more time, little longer time than the simple memory system. So first one should be completely ruled out. To access the virtual memory, definitely system takes more time. Processes can be given protected address space. No. Protected address space, private address space, or no protected address space, which is defined by the memory management unit, MMU. Okay, our virtual memory is going to nothing to do with this. Processes can be given a protected address space, which actually has to be taken care by the memory management unit, but not the virtual memory. Linker can assign the address. Straight away I need to rule out. Linker and virtual memory, there is no connection. Linker is a process which actually is going to perform some linkage in between the current executing process with some files. It is going to link. Now, why virtual memory comes into the picture? No. Programs larger than the physical memory size can be run. This is what the importance of the virtual memory. This is why we use the virtual memory. Now understand, there is a simple reason behind it to say D is correct, because let us say let us take an example of your own RAM size. What is RAM size? RAM size may be 6 GB. Your RAM size is equal to 6 GB. Okay. Your hard disk size is equal to 1 TB. What is the fundamental rule of executing a program? In order to execute a program, that program must be residing within the main memory, right? Unless otherwise, we will not be able to execute a program. It's a simple fundamental rule that we have learned before we started learning anything in the computer science. Computer system always states that if you want to execute a program, that program must be made available in the main memory. Okay. Now I will tell you one thing. Let us take a 4K video. Let us play a game. Let us say there's a PUBG game. The game size, let us say it is 8 GB. The 4K video is 12 GB. Okay. Now understand. This game size, what you're playing, or this 4K video what you're watching actually is more than that of the size of the available main memory. But how still you are able to execute the program? How still you are able to watch that movie? Because of the concept of the virtual memory. Virtual memory will allow the user or a programmer to access the only desired pages, desired portions of the entire program. In the virtual memory, you don't need to bring the entire program into the main memory. Only those frames, only those pages which are required concurrently can be brought into the main memory. So the total 12 GB can be kept in your hard disk, from which the frames, whatever those are useful right now, will be brought into the main memory. So virtual memory's fundamental objective is to make sure that the program larger than the physical memory size can be run in a system. This is the fundamental use. Assume that there are 3 page frames which are initially empty. Now this is the numeral. We will solve it. If the page reference string is 1, 2, 3, 4, 2, 1, 5, 3, 2, 4, 6. The number of page faults using this optimal page replacement policy is, we need to calculate the total number of page faults in optimal page replacement policy. What do you mean by optimal page replacement policy? In the optimal page replacement policy, the page which is not going to be referenced in the near future will be replaced. I will tell you right now. Now see how many page faults will occur. Total number of pages, sir. Total number of physical frames is equal to 3. Right? 1, 2, 3. Initially, because initially all the frames are empty. Now, operating system wants 1, rather program wants 1. 1 will be kept here, and this is the page fault. I will write it 1, 2. For 2, we don't require any page replacement because 3 slots are available. But this also leads to 1 more page fault. 3, yes, there is 1 more page fault. So after the first 3 references, since the main memory is completely empty, all the 3 frames are empty, we will have 3 page faults. Right then, 4. In order to place 4, what should I replace? We need to look at in the forward direction. In the forward direction, 2 cannot be replaced because 2 is being referenced in the very next axis. 1 also is being referenced in the very next axis. And 3 is not being referenced in the very next axis because before 2 and 1, there is 3. So 3 can be replaced. So this 3, and the place of 3, I can place what? 4. Okay, which is going to add 1 more page fault. Right? 2, there is no page fault. 2 is available. It is the page availability. Page availability is not a page fault. Then 1 also is available. It doesn't lead to a page fault. Then 5. I need to keep 5 in this frames. In the current main memory, the available 3 frames hold 1, 2, and 4, but not 5. So I need to replace one of these pages. Which page must get replaced? Now look in the forward direction. 3, there is no 3. 2, of course there is 2. I cannot replace 2. And 4 also is there. So I cannot replace neither 4 nor 2. Okay. So I can replace 1. So in order to place 5, I can replace 1. So the next thing is 1. There is total 5 page faults. Then I need to place 3. In order to place 3, which should I replace? I cannot replace 4. I can replace in between 2 and 5. So what I do is I will take randomly, excuse me, what I'm placing right now. In order to place 3, I cannot replace 2 and I cannot replace 4. I need to replace 5. Yes, 5 must be replaced here to keep 3. So which will add one more page fault. Okay, 1, 2, 3, 4, 5, 6. Then 2. Okay, 2 is already available. Then 4. 4 is already available. The total number of page faults is equal to 6 here. Okay, that what is the total number of page faults? The total number of page faults is equal to 6. Consider the system with a byte addressable memory, 32-bit logical address, 4 kilobyte size, and a page table entries of 4 bytes each. The size of the page table in the system in the megabytes is equal to, that is, let me tell you, we need to find out page table size. This page table size can be given as number of pages into one entry size. Page table size can be size. That is equal to, what is the total number of pages? In order to find out the total number of pages, we need to divide the total secondary memory with the page size. Total secondary memory is equal to 2 power 32 divided by total number of pages is I will say TP. TP meaning total pages is equal to total virtual memory divided by total page size. Page size is equal to 4 kilobyte, right? 4 kilobyte meaning 2 power 12. So the total number of pages will be equal to 2 power 32 divided by 2 power 12, which is equal to 32 minus 12 is equal to 2 power 20. Total number of pages is equal to 2 power 20. So page table size is equal to 2 power 20, which is the total number of pages, into one entry size. What is one entry size? One entry size is equal to 4 bytes as given in the question. So the page table size is equal to 2 power 20, 1 MB into 4 bytes. That means 1 M into 4 bytes is equal to 4 MB. 4 MB is the correct answer in this case. Next question. Consider the 6 memory partitions of size 200 KB, 400 KB, 600 KB, 500 KB, 300 KB and 250 KB, where KB refers to the kilobyte as usual. Those partitions need to be allotted for 4 processes of sizes 357 KB, 210 KB, 468 KB and 491 KB in that order. If the best fit algorithm is used, which partitions are not allotted to any process? What is best fit? Best fit meaning, see, here the thing is, there are 6 memory partitions. Each partition size is 200 KB, 400 KB, 600 KB, 500 KB, 300 KB and 250 KB. Now in the best fit, whenever there is a request coming in, we need to take that request, put into one partition which is smallest enough, smaller than any other partition, which is sufficient to hold us. In the best fit, whenever there comes a request, whenever a process comes, the process size is equal to 357. So in order to keep this process, we need to find out a partition which is smaller than any other partition and is also sufficient to hold us. Okay, so in which I will say, I will draw these 6 partitions. First partition is 200 KB. Second partition is 400 KB. Third partition 600 KB. Fourth partition 500 KB, fifth partition 300 KB, and the next partition is 250 KB. Now take 357. So you need to keep 357. We need to find out the smallest partition which can accommodate 357. So 357 can easily be accommodated in 400. So I will give 357, the process which is of size 357 to 400. So 400 is the only partition which is smallest and also is capable of holding 357. And the next thing is, where is this? 210 KB. So in order to keep 210, 200 is not sufficient, rather 250 is sufficient. So I will keep 210 here. So 400 and 250 are consumed already. Next thing is 468 KB. In order to keep 468 KB, I will use 500. So 468 is given to this. And next thing is 491. Then what should I use? In order to keep 491, I need to use 600. Okay, 491 is allotted this. Now, which are the partitions are not allocated to any other process? Here the thing is, you can clearly see 200 and 300 are not allocated to any process during this allocation, because first of it always requires the smallest partition, the smallest chunk of the main memory which can actually accommodate the incoming process. Okay, so in which this 200 and 300 will not be allocated to any process whatsoever. With which we have come to an end of this session, and yeah, do register to Vision Gate 25, 25 and 26. If you're gate aspirant for 2025 and 26, Byjus exam prep already started the vision course. If you enroll it, and the total, you will get live classes, recorded lectures, study material, practice quizzes and mock tests, whatnot. You will be provided with the total package to clear the gate exam quite comprehensively in the very first attempt itself. So I request you people to get enrolled into the Byjus exam prep vision course and do not miss this. And also there coming one very good event on your way, that is the scholarship test. Byjus exam prep is actually conducting its scholarship test on the 10th of the March and offering 90% off for those people who actually can score good. So do not miss this opportunity. You will be provided with a scholarship and off for all the courses in the Byjus, the complete Byjus platform, and you will be getting a comprehensive coaching for Gate 2025 and Gate 2026. Do not miss this opportunity. And that's it for the session. Anil Prasad Sorampudi signing.